Hello guys, in this video I will cover the topic of pH scale, that is a topic that we start the previous class. In this video I will cover what is pH, how it's calculated, if you have the concentration of hydrogen ions, how can you calculate the hydrogen ions if you have pH, this is the opposite operation, and what is pOH and how to calculate the hydroxide ion concentration. So let's start with pH. pH is the inverse logarithm of the hydrogen ion concentration. Remember, these brackets and hydrogen ion inside represents the hydrogen ion concentration. So the pH of a solution is equal to the negative logarithm of the hydrogen ion concentration. For example, here, and remember, hydronium ion it's the same as hydrogen ion for this type of exercises. So we can say that this is the same. They are equal. And you can calculate the pH using the formula. pH is equal to negative logarithm of the hydrogen ion concentration. So it will be negative logarithm of 1 times 10 to the minus 8. And the pH will be equal to, let's do that in the calculator. It will be negative logarithm of 1 times 10 to the minus 8. And the answer, 8. pH of 8, similar to, for example, seawater. Another example, hydrogen or hydronium ion concentration equals to 4.7 times 10 to the minus 2 molar. Remember again that this is equal. So it will be pH equals to the negative logarithm of 4.7 times 10 to the minus 2. And it will be, let's do that. 4.7 times 10 to the minus 2. And this is equal to a pH of 1.32. And that's the answer. Okay, so that's how you calculate pH. Remember, it is equal to the negative logarithm of the hydrogen ion concentration. Negative logarithm of the hydrogen ion concentration. But what happens if you have pH and you want to know the hydrogen ion concentration? Because the formula of pH includes this, and it includes a logarithm with base 10. So if you want to go from pH to hydrogen ion concentration, you can use the opposite of a logarithm base 10, which is an exponentiation with base 10 with negative pH at the exponent. This is this formula. Concentration of hydrogen ions will be equal to 10 raised to minus negative pH. So for example, here we have two exercises. The first one, we have a pH of 6.5. So the hydrogen concentration will be equal to 10 to the power of minus pH, which is 6.5. So let's do that. It will be 10 raised to the power of negative 6.5. And I got as an answer that we have a hydrogen ion concentration of 3.16 times 10 to the minus 7 molar. And let's do the same with the lemon juice. The lemon juice, it's an acid. It is 2.37. And let's calculate the hydrogen ion concentration. It is equal to 10 raised to the power of minus pH. So it's 10 to negative 0.37. Let's do that in our calculators. 2.37. And it will be equal to 0.00443. If you use your if you transform this into scientific notation, it will be 4.3 times 10 to the 1, 2, 3 minus 3. And if you remember, if a value is greater than 1 times 10 to the minus 7, if it's greater than this, it's an acid. And this number, it's an acid because it's equal to 0.0043. And this number, it's equal to 0.0000001. That number is clearly greater than this. So if your hydrogen concentration is greater than 1 times 10 to the minus 7, it will be an acid. And you know that lemon juice, it's an acid. Great. So in a similar way, pH is slightly acidic because this number is 0.00000316, and this number is slightly greater than this. Therefore, the milk is slightly acidic. Also, you know that because it's less than 7, which is neutral. And if the pH is less than 7, it will be an acid. Excellent. I hope that you understood this. With these numbers, I'm referring to the hydrogen ion concentration. With the pH, you can look at this and determine if it's an acid or a base. Both of these are acids. Now, pOH. What is pOH? Well, pH is the hydrogen potential. pOH is the hydroxide potential, and it takes into consideration hydroxide ions. It's exactly the same as pH, but instead of hydrogen, it takes into account the hydroxide ions. And there is something important. If you combine pH and pOH, the answer will be 14. For example, um, I'm going to do an example of this in a moment, but look at this. If my pH is 1, my hydrogen ion concentration will be 10 times 10, 1 times 10 to the minus 1. If it's 7, it will be 10 to the minus 7. If it's 14, the hydrogen ion concentration will be 10 to the power of minus 14. And if you look, pH is increasing in this direction. pOH is growing in the opposite direction. Both of them have a coincidence in the neutral value. pH and pOH are both 7 in a neutral solution. So it will be 7 plus 7 equal to 14. That not only happens in the center. For example, if you add 1 and 13, or if you add 12 and 2. So the pOH and pH addition will always be 14. This is very similar to the water constant. In the water constant, we were considering these two. Remember, water constant, it's equal to multiplying the hydrogen ion concentration times the hydroxide ion concentration, and it is always equal to 1 times 10 to the minus 14. For example, let's take the extremes. Hydrogen ion concentration of 1 times 10 to the minus 14 equals to 1 times 10 to the minus 14. And let's go to the other extreme, to the most basic. A pH of 14 means that you have a hydrogen ion concentration of 10 to the minus 14. And it's a hydroxide ion concentration of 1. 1 times 10 to the minus 14 equals to 1 times 10 to the minus 14. So the water constant will always be this. And this is similar to this, the number 14. Okay, so now let's see how, let's calculate some pOH for different solutions. Remember, this is the formula. And let's calculate the pOH of a solution whose concentration of hydroxide ion is equal to 1 times 10 to the minus 2. In this case, we are not going to use this because this is for pH. For pOH, the numbers are inverted. This is 14, 13, 8, 7, 6, and this will be 2, 1, and 0. Okay? It goes the other way. This is for pOH. So let's see. The formula says that pOH is equal to the negative logarithm of the hydroxide ion concentration, 1 times 10 to the minus 2. And it will be, let's see, let's do that operation, negative logarithm of 1 times 10 to the minus 2. And it's a pOH of 2. Let's do another example. Hydroxide ion concentration of 8 times 10 to the minus 13. So it will be pOH equals to negative logarithm of 8 times 10 to the minus 3. So it will be negative logarithm of 8 times 10 to the minus 3. And it is a pOH of 2.1. Let's see. Let me see if I'm correct. Yeah, apparently it is correct. So let's see if this makes sense with the previous table. 1 times 10 to the minus 2, 1 times 10 to the minus 2, and it has a pOH of 2. Yes, it is a pOH of positive 2. And what happens if you want to go from pOH to hydroxide ion concentration? Well, in a very similar way, you can go the other way using an exponentiation with a base of 10, and in this case with negative pOH as the exponent. Very similar to the hydrogen ion concentration calculus. And it will be, for example, this milk of magnesia. But wait a moment, this is pH, it's not pOH. So you can do two things. You can calculate the hydrogen ion concentration, which will be equal to 10 times elevated to the power of minus pH, which will be 10 to the minus 10.5, and that will be, let's see, 10 raised to the power of minus 10.5, and it is equal to 3.16 times 10 to the minus 11. And then you may remember this. With that, you can calculate the hydroxide ion concentration, which will be given by the division of the water constant by the hydrogen ion concentration. Therefore, the hydroxide ion concentration will be equal to, let's say, it will be 1 times 10 to the minus 14 divided by 3.16 times 10 to the minus 11. 1 times 10 to the minus 14 divided by 3.16 divided by, times 10 to the minus 11. And it is equal to 0.00032, which is 3.2 times 10 to the minus 1, 2, 3, 4, minus 4. Okay, that's a way to calculate that. I'm gonna rewrite that formula here to make a space. And it says that hydroxide ion concentration is equal to the water constant divided by the hydrogen ion concentration. I solved this formula for hydroxide ions. And another way that you can solve this is simply looking at this. pH plus pOH it's equal to 14. pH, I'm going to place to draw a line to separate the procedures, plus pOH it's equal to 14. So if I solve, I move this to the other side, it will be pOH it's equal to 14 minus pH. This is 14 minus 10.5. And that is equal to a pOH of 14 minus 10.5, 3.5. And then you can use this formula. Hydroxide ion concentration equals to 10 to the negative 3.5. And that's equal to, let's see, 10 raised to the power of negative 3.5. And that is equal to 0.00032, which is 3.2, 1, 2, 3, 4 times 10 to the minus 4. And that's the answer. I prefer this second formula. That formula, it's easier because you are not using exponents, you are going directly to this. So I encourage you to do that formula, to use that formula to solve the exercises like this. In any case, let's try to do another example that is very similar to that. And it will be, instead of magnesium milk, it will be another type of milk. It is, give me a moment, household ammonia, which has a pH of 11.9. And I have it in the next slide. It's very similar to this slide. But now we have household ammonia. And remember the same. pOH is 14. Sorry, the addition of pH and pOH is 14. So we have the pH of 11.9. We can calculate the pOH. pOH is equal to 14 minus 11 minus pH. And that's 14 minus 11.9. So the pOH is equal to 14 minus 11.9, 2.1. And then hydroxide ion concentration will be equal to 10 to the power of minus pOH minus 2.1. And that is 10 to the power of negative 2.1. That's equal to a hydroxide ion concentration of 0.00794, which is 7.94 times 10 to the negative 1, 2, 3. That's the answer. And with this, I finish this video. Thank you for your attention, guys. See you.